Okay, so in this lecture, I'd like to tell you about the so-called isomorphism theorems in group theory. So different people number them differently. For me, there are three basic isomorphism theorems that I'm going to tell you about. I'm not going to describe the proofs, but if you look at the proofs, the proof of the first one is really straightforward once you understand the statement, and then you somehow, it's like snowball from the first to the second to the third. You just apply what you've just learned in the previous one. You try to apply it to prove the next one. But the most important thing is to get comfortable using these isomorphism theorems, because they are really the basic tools in group theory, and you see that if you study the proofs of Sylow's theorem, for example. Okay, so three isomorphism theorems. Okay, so the first isomorphism theorem is the following. So first iso theorem, assume phi from G to H is a homomorphism of groups, then phi factors through, so we have the following diagram, G to H by R phi, that's what we have by hypothesis. I claim there's a factorization to G modulo the kernel of phi. Here I have the projection, right? Anytime I have a quotient of a group, I have a projection that's taking G to the coset G kernel of phi. Okay, and then I continue here, so factors through phi bar as follows. I'm claiming that there exists this map phi bar, and phi bar is an isomorphism between G modulo the kernel of phi and the image of phi. So all this is saying really is that first we can factor through the modulo the kernel, and then we are saying that this map phi bar is injective. Once we know it's injective, it's obviously surjective onto its image. Now let's note an important consequence of this. In particular, if our starting homomorphism phi, if phi is surjective, then G modulo the kernel of phi. If phi is surjective, then this phi bar is necessarily also surjective, and then G modulo the kernel of phi is isomorphic to H. Okay? So in general, G modulo the kernel of phi is isomorphic to the image of phi, but if phi is surjective, then it's the image of phi is H. Okay? And so I think the trickiest point in proving this is really how to start, how to think of how to define this phi bar. But there's only one way you could do this. You want to say, where does this coset map? And you define this coset to map to where this representative G maps. That's the only thing you can possibly think of. And then the only thing that we have to check is that that is well defined. So note phi bar. So we define phi bar by phi bar of G kernel of phi. This coset is phi of G, and this is well defined, since if I have G1 kernel of phi equals G2 kernel of phi, that means that G1 and G2 are two representatives of the same coset. Then I have G1 equals, so this is saying that G1 is an element of the coset G2 curve phi. So then G1 is G2 times K for some K in the kernel of phi. And then phi of G1 is equal to phi of G2K is equal to phi of G2 phi of K, because phi is a homomorphism. And this is equal to phi of G2 because since K is in the kernel. Since K is in the kernel. Okay? So that shows that phi is well defined. So I will not say more about the proof. I think I've done the hardest part of the proof. The other steps are similar or arguments of less than or equal difficulty. Okay. Let's go on to the second isomorphism theorem. Before we state it, we need a lemma, which is useful to know about and is something that can often be given as a homework or exam problem. So assume H n subgroups of G, and we assume that one of them, n, is normal in G. Then the product H times n, which by definition this is the set of little h and big A, of little h, little n, such that little h is in big H and little n is in big N, is also a subgroup. Oh, gee. So this is very useful to know about, not just for the second isomorphism theorem that I'm about to write down, because this is a procedure for producing a new subgroup from two existing subgroups. If you know one of them is normal, you're allowed to take the product in the sense defined here to get a new, bigger subgroup. Okay, so how is this lemma proved? Well, I take H1, N1, and H2, N2 in Hn. That's what two elements in H times N look like. So H1 and H2 are in H, and N1 and N2 are in N. And now we want to show that H1, N1, H2, N2, we want to show that this one is also an element of H times an element of N. Now, the way we write it initially doesn't look so good, but we need to use the fact that N is normal. So we want to insert an element of N times its inverse to make this in the way that we want to. So now it's always a little bit difficult to remember exactly where you want to insert the inverses. So what we can try to do is H1, N1, H2, N2, H. No, so this is not working. So let's see. We want to use the fact that H and H inverse, this is in N for all H in H and in N. That's the our assumption that n is normal. Well, I mean, this we even know for all h and g, but certainly for all h and h. So we do h1 n h1 h2 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 inverse n1 h2 n2. Let's see, what have I written here? So I have h1 h2. This is an element. This is in H. It's a product of two elements of H. Now, this N2 is an element of N, and now this H2 inverse N1 H2, well, that's of this form. Just I have taken H to be H2 inverse. So this is in N, and this is in N. And so the whole part here, the whole circled part, is in N, because it's the product of two elements of N. So I have managed to rewrite it as an element of H times an element of N. Now I have not cheated, because this is exactly what we have here, except that I have inserted H2, H2 inverse, and that is the identity. Okay? So this shows, so hence, H1, N1, H2, N2 is in H times N. And let's leave it to you as an exercise. Show that Hn in Hn implies that also the inverse is in Hn. So with your help of doing the exercise, then I've shown closure under multiplication, you show closure under inversion. Together we have completed the proof. Okay, so now with the help of this lemma, let's state the second isomorphism theorem. So same assumptions as lemma. So I have my group G, I have a subgroup H, a subgroup N, and N is normal in G. Then Hn, so by the lemma, this is a subgroup. So it's, in particular, it can be considered as a group in its own right. Now, this will have N as a normal subgroup. If N is normal in the big group G, it's normal in any subgroup of G containing N, because to be normal in here requires less to be verified. This is isomorphic to H divided by H intersect N. So we are saying that H intersect N is a normal subgroup of H, and that we have an isomorphism like this. And I've written it like this with an arrow like this, because you can prove this by constructing a homomorphism and finding the kernel and then applying the first isomorphism theorem. I won't do that. I think it was more important to work out the proof of this lemma, but this is, in any case, the statement of the second isomorphism theorem. Now we come to the third isomorphism theorem. So okay, so now I have, assume I have a normal subgroup N of G. Okay, so now what I want to do is I want to get into a situation where I have a double quotient. So assume N is normal of G. then sometimes this is stated as what I'm going to say as part of the first isomorphism theorem. Then, so the subgroups of G mod n are in bijection with subgroups of G containing n. And so let's suppose, and they have the form, so I have G mod n. Then if I have a subgroup, it might look like K mod n. Okay. So every subgroup of G mod n will look like K mod n. And K mod n in G mod n is normal if and only if K is normal in G. And if K is normal in G, then we have the following isomorphism. I can do G mod n modulo its normal subgroup K mod n. And now forget for a second that we are talking about groups and quotients and so on, and think that this is just a fraction. What would you do? You would cancel out and say that this is G mod K. This makes sense, right? Because K is normal in G, so I was allowed to do that quotient. N is normal in G, I'm allowed to do this quotient. And we said that if K is normal in G, that means that K mod n is normal in G mod n. So I'm allowed to mod out G mod n by K mod n, and the theorem is saying that you get exactly G mod K.